Okay, good evening everyone, and welcome to the sixth session for the course Basic Real Analysis. So today, with the most of the problems what we'll be discussing today is based on differentiability of functions. Okay. Okay. So to begin with, let's start with this problem. So suppose you have been given a function f from a b to r, which is differentiable. Okay, such that the derivative f prime is bounded on ab. Okay, so you have to prove that f is uniformly continuous. I think I discussed this in the last. I discussed some other problem where you established something like this. Do you remember?
Yes.
Yeah, so here what do you do? How did we prove it? So in fact, it is much more. So it's not just uniform continuous, but it's basically Lipschitz continuous. This is what you can show using the boundedness of the derivative. So can you recall what did we do?
Sir, use this definition of the differentiability
Okay, you want to go with the notion differentiability. Okay, and then
and using this boundedness, then we'll be able to.
okay, yeah, okay, but there you will have to use.
After is Lipschitz, then uniformly continuous.
Yeah, but there, the definition you can do by that. Okay, so if you want, okay, let's try with that only. So it's saying that f prime of x is basically limit x going to, or let's say h goes to 0. Let me write it this way: x going to x naught, f of x minus x naught. Yeah, so this would tell you that this difference if 0 less than, right? And then what you can do is you can now you just look at this term. So using triangle inequality, you can say this is less than equal to epsilon plus f prime of x naught, right? And you know that this is a bounded quantity, right? So this will give you this is less than equal to some c. Okay, so over here the restriction is 0. Okay, but using this you won't be able to conclude, right? So okay, anyway, so this, and from here you can say this is x naught less than c times x minus x naught if 0 is less than x minus x naught less than delta, right? So over here now you can see this constant c is depending on x naught, right? This term. So directly, like, this is not a correct way, right? Because you, if you want uniform continuity, this is what you were saying, or
Yes, sir.
yeah, but okay, so the but actually some way you have to make this constant to be uniform with respect to this x naught, and for that what can be done? Just a second.
Sir, by contradiction.
No, proof I have. Like, you just use mean value theorem, you will get it.
Hmm.
That's not that is the simplest way. Just use mean value theorem because you have done sufficient work over there. So since you know the theorem, you can directly use it. Okay. So as far as solution is concerned, you can do it using mean value theorem. But here, like what I was just thinking how to make this constant independent. Oh, okay. Sorry.
Sir, this is
It
positive,
is
sir.
not constant dependent, right? So, okay. So let me. So this I'm saying this is less than equal to m, right? I'm using the bound of the derivative. Yeah. So here now this m is now independent of x naught. So this is less than equal to epsilon plus m, and this is, let's say I'm calling it c. Okay, so now I'm saying this is c times x minus x naught if my x is in the neighborhood of this x naught. Okay, so now this I can say this is less than epsilon if my x minus x naught. Okay, just a second. Oh, so here I already have one delta because of this differentiability. Okay, so this is less than epsilon if this is less than uh, epsilon by c. Yeah, but again there is one more problem actually. So this delta over here uh, is also depending on the point, right? This delta, so this is also somewhere depending on the point x naught. Okay, so you should not forget this. So anyway, I think this approach, like, you'll have to change a bit probably, and then you can get the answer, I think. Okay, but I'm not sure how to do that. But at this point, this is clear that this solution is not going to help in this way direct using the definition probably. Okay, so let's write the solution what I know. Okay, but you can think, I think some variation can be done over here to get the answer. Okay, so as of now let's not go into it. Should I leave it or should I rub it? I think it's no, not needed. Okay, let me just rub this off. But I think you can do the proof by changing a bit in the argument. Okay, so let's write what proof I was saying earlier. So using mean value theorem. So since I know that the function f is given to be differentiable, okay, and hence it is continuous. So okay, so if you want here, you can assume it's continuous on this closed AB interval. Okay, so let me add that also. Okay, let leave it. Now f using mean value theorem, we have, or there exists some c in, let's say, AB such that f prime of c is equal to fb minus f of a. Okay, so I'm choosing any xy. Let me restrict to any xy. So let xy belong to this interval AB. Okay, then the function f from xy to r is continuous and also and differentiable on the open interval xy. So by mean value theorem, there exists some c in xy such that mod of fx, sorry, f of x minus f of y upon x minus y is equal to f prime of c. Okay, and then I'll just take mod. So fx minus fy is less than equal to f prime c times x minus y. So it is equal to, now I know this is given to be bounded, this derivative. So I'll say this is less than equal to m times x minus y. Okay, so this tells you this, that the function f is Lipschitz continuous and hence uniformly continuous. Okay, so this is the easiest approach Okay,
Sir, what is Lipschitz continuous function, sir?
this like if you have this kind of form that fx, sorry, fy is less than equal to, so if there exists some L such that fx minus fy is less than equal to L times mod x minus y, then we say that this is a Lipschitz function.
Lipschitz continuous, sir.
Okay, so is like this is what we call, if you want you can omit this. Okay,
Yes.
Lipschitz implies continuity, so sometimes you can also say Lipschitz continuous. Anyway, okay. Okay, so let's go to the next problem. So the next problem is
Sir,
that
sir, when we are trying to, sir, prove from the definition,
definition.
sir, definition of the differentiability. So, sir, the f is differentiable on the whole interval, sir, na?
True.
So we can choose any point, sir.
That's
Why
true.
we choose specific x naught, sir?
Yeah, so but that delta what is coming, the way I was writing, so I was using the definition of the limit, right? So now you choose any x naught. The delta what I was getting was depending because x tending to x naught. So delta
Sir,
is,
x tends to y, na? If f is differentiable, then limit x tends to y, f of x minus fy upon x minus y.
yeah. So you are using differentiability of y at the point y, right?
Sir, y is any sir point in that interval.
Yeah, but the delta what you're getting, it will change if I'm using the definition of the limit, right? So for each of the point, won't it? Okay, so if you do you want to discuss it now?
No, sir.
I mean, if you want, I can go on with it.
No, sir.
Okay. Okay, then maybe at last we'll discuss on that. Yeah. Okay, so now the next thing is that what about the converse, kind of converse? So uh, suppose f from AB to R is a differentiable function which is uniformly continuous. So does this imply f prime is bounded? So we said that if its derivative is bounded, we know it's uniformly continuous. So what about the converse?
Sir, I think it is true, sir.
It is true. So how should we proceed proving this?
Using the definition of, sir, Lipschitz functions.
No, here it's given to be continuous. Okay, if you want, you can assume Lipschitz also. But for Lipschitz also, it's not going to be true. For Lipschitz also. Okay, so okay, let's. So do you want to prove it? So how should we go? If you want to prove. So you are saying, what did you say? So see, you want to get some bound on this. If you want to show that this is bounded, that means you have to get some bound on this. By definition, you know that this is equal to, let's say, limit h going to 0, f of x plus h minus f of x upon h, like this kind of thing, right? Now, if your function is given to be uniformly continuous, you know that f of x plus h minus f of x is going to be okay, so let's assume that it's Lipschitz continuous at first. Okay, so then this would say this is less than equal to L times mod h. Yeah, so this will tell you, then I think you will get it to be true. So I think for Lipschitz it will be true, right? So we got this one. Yeah, so this
Yes,
is true
sir.
for all h. Okay, and then we can substitute it, so the limit is always going to be bounded by L.
Yes, sir.
Yeah, so for Lipschitz I think you can say, but for uniform continuity you don't have this
Yes, sir.
kind of.
Yes, sir. Yes, sir.
Hmm?
This need not be.
Okay. Okay. Okay, so we, so now, okay, so for uniform continuity we will have to look for some counter example, right? So you can look at this function. So if, let's define it 0 1 to r. Okay, so now we want to find the counter example, so we want the derivative should be unbounded. Okay, so I'm choosing this kind of function fx equal,
X to the power minus 1 by 2.
yeah, x to the power minus 1 by 2. But here the function itself, so it won't be uniformly continuous, I guess. Okay,
Sir,
so
X to the power 1 by 2, na, sir. Take.
yeah, so just take root x.
Ah.
Yeah, so now you can prove. So clearly let's, so first we need to check whether it's uniform continuous or not, right? So
Yes, sir.
so did I delete in the last, I don't think so. Okay, how do you prove this is uniformly continuous?
Sir, by sequential criteria.
Okay, okay, so let's do that. So you're saying let xn yn be any sequence in 0 1 converging to such that mod of xn minus yn goes to 0. So f of xn minus f of yn, if you do, so what do you get? This is root of xn minus root of yn. So how will you conclude now? So you'll have to use the root. So what do you think? Anyway,
Sir,
now,
yes, sir, rationalize, sir.
so but there would be some problem. N xn minus yn, right? Now how will you bound this one? What if your xn and yn are converging to 0? I mean, so how will you get lower bound for this?
Sir, by the triangle inequality.
So no, okay, so what, okay, what kind of inequality? Root xn, what will you do? So suppose I am saying let's take xn equal to 1 by n and yn equals to 1 by n plus 1. Okay, in this case 1 by root n plus 1 by root n plus 1, this is going to 0. So how can you find I mean a lower bound for this? Can you say this is greater than equal to some constant? Because I want to use this is less than equal to some constant, right? Times xn minus yn. Yeah, so you won't be able to get this lower bound.
Sir, lower bound is always 0, na, sir?
Sorry?
Lower bound is 0, sir.
Yeah, I'm just saying that how to bound this one. This will blow up if you're, anyway the numerator is also going to be 0, but the question is how do you, if you want to explicitly find the bound for this, you won't be able to get it, right?
Yes, sir.
So here what you can do is,
Sir, use this differentiability, sir. If we are able to, sir, so that the function is derivative of the function is bounded.
but we are searching for an example where the derivative is unbounded.
Yes, sir.
The derivative is unbounded, But here what you can do is you can do this thing. So you can say this, let's look at this term. Okay, I don't know, is there some delay in writing? I feel like I am writing but I'm not able to see it.
No, sir. Perfect, sir.
There is some lag, I feel. Okay, you are able to see whenever I write. So did you see x minus y just as of now?
Yes, sir. Yes, sir.
Okay, then I think it's just my system problem probably. I don't know what is happening today. Okay, anyway, but that would be recorded. I don't know. Okay, let's see, let's wait for a few minutes. So what I was saying is that you can say this x minus y square is what? This modulus. This is x minus y, x minus y. Now this x minus y I can bound it by x minus y, x plus y. I can do this, right? This I am bounding by x plus y because both are positive. Here we are taking difference, and this is because xy belong to 0 1. So x minus y is going to belong to minus 1 comma 1, right? And x plus y, so I mean this is always going to be greater than this. Okay, x minus y. Yeah, so then you can say this is equal to x square minus y square. Okay, so this will tell you that this mod x minus y is less than equal to x square minus y square. Sorry, this is square. Okay, now you can say then you get x minus y is less than equal to yeah, so this is x square minus y square, then 1 by 2. So if I use this estimate over here, what I get is this would be xn minus yn square root, right, whole to the power 1 by 2. And then you know that this goes to 0. Okay, so this would imply that mod of fxn minus fyn, this goes to 0 as n goes to infinity. Okay, so this shows that f is uniformly continuous. Okay, but you can clearly see the derivative. You already know that f prime of x is given by 1 by 2 root x, and you know this is unbounded in 0 comma 1. Okay, is this fine?
Sir,
Yes.
sir, we can also use the result, sir. F is continuous on the open interval B, sir. And limit extends to a plus and limit extends to b minus of f exists finitely, then
Yeah. Okay.
only from the continuous answer open interval.
Yeah, sure. Okay, so if let's do that also. I mean, let's write it that one as well. Okay, so this is, let's say, one way of doing it, or so the second argument would be, as you are saying, so fx equals root x is continuous on 0 1. Also, actually here you can just say this is continuous on close 0 1. Okay, so this would imply f is uniformly continuous on close 0 1. Okay, but the thing is, yeah, this would be much more easier, because here if you want to use sequential criteria, you will say xn goes to x naught, then you will say root xn goes to root x naught. Okay, and this will imply continuity. Okay, anyway, and then this will tell you f is in particular uniformly continuous on 0. Okay, so this may be another way of looking at it.
Sir,
okay, yeah.
Sir, a differentiable function is bound, sir, derivative of sir, function is bounded on a sir, closed interval. Is this true, sir?
Sorry. Derivative
Derivative of a function on a closed interval is bounded.
No.
Under root x, sir.
No.
Yes, sir.
If, see, that's where f prime. So if you are saying if f prime is given to be continuous, then that's why this sometimes you say that f is in C1. That means f prime is continuous.
Yes, sir. Yes, sir. Got it.
If that is the case, then you can say.
The under root x is example, sir. There. Under root x, sir.
Under root x is not.
But f dash x is unbounded.
The derivative is not continuous at 0, right?
I am, sir, telling you counter example, sir.
Oh, okay.
Yes.
But anyway, like when you are okay, so I think it's not a perfect counter example because you were talking of f defined on closed interval. So your f prime is not defined on 0, 1. So if you want this derivative to be bounded, then I mean on compact set, if you are saying, in this case the domain is not compact, right? Okay.
So what can be the counter example?
Counter example can be, so you want f to be AB, you'll have to think such that f prime AB is not continuous. Okay, so maybe what you can think is, let me think, it's not continuous. So you want to find a function which is differentiable but the derivative is not bounded. On a compact domain. So what could be the example? It should be easy. Yeah. How differentiable function? It cannot be polynomial. It cannot be sine x sine 1 by x. This one, yeah, this is the example, right? X sine 1 by x. So f of x. So let me define f. So maybe let me write it properly. So if you consider 0 1 to r such that f of x is equal to x times sine 1 by x. Okay, so here this function f is, you can clearly see f prime of x. If you want, it would be x. Okay, so first let me show. So this is this and 0, x not equal to 0 and x equal to 0. So let me check the derivative. So limit at 0. So you know that at non-zero point it is differentiable, so there is no issue at that point. So let's check differentiability at 0. So limit h going to 0, f of h minus f of 0 upon h. Okay, so let's put a square over here. Okay, so then it will be limit h going to 0, this would be h square sine 1 by h upon h, right? So this is going to be 0. So f is differentiable at 0 and at any other point. So f prime of x would be x square cos 1 by x times minus 1 by x square into 2x plus 2x sine 1 by x if x is non-zero, and it is 0 if x is 0. Okay, so will it be, so it would be 2x, but it seems to be continuous. This is continuous.
Why is there 2x, sir? F dash x, sir. X square cos 1 by x into minus 1 by x square, then where
Oh,
it is
okay. Sorry. Yeah. Then you are getting this, right? Now this is not continuous, right?
Yes, sir.
So, okay, so the question was, so okay, so this f prime.
These are bounded, sir.
Yeah, that's what I was thinking, but this is bounded. Okay, so let me write f prime is not continuous first of all, but here the thing is that it is bounded, the derivative. Okay, let me think of some other example then. Okay, so let me, this example is for example for differentiable function whose derivative is not continuous. Okay, but we want differentiable function which is on compact domain and which is unbounded. Okay, so let's look at for function which is on compact. Okay, then I think, okay, so I think it can be true. Okay, so we are saying that f prime defined on AB to R is bounded. This is the question. Now your guess would be that I will look for some function, let's say in AB to R, which is not bounded. Okay, if it is continuous, then it's going to be bounded. So let's take some example. So give me some example which is unbounded on a compact domain. Okay, so
non-continuous function can also be bounded, na?
Sorry?
So non-continuous function.
Yeah. So that's why I'm asking for a function which is, if it is continuous, then it is going to be bounded. So we have to look for a function, obviously in the set of discontinuous function, right? So I'm just thinking, what are the function which is unbounded in a compact domain? Going to 0, 1. Yeah, that is the only option. So we have this kind of function. The point is that I want my derivative to be this kind. I mean, it should be of this type. So if I take f, okay, then I think, just a second, f of x equal to, okay, root x if I take, then 1 by root x. Let me see. Then f at h minus f at 0. So let's take, okay, so any half less than 1 will not work. So what if I take log of x equal to 0? So I'm defining on 0, okay, 0, 1, let's say. Okay, then f prime of x at, so let's check differentiability at 0, h log of h upon h. So this limit by h, it does not exist. I mean, it will blow up. Yeah.
So what if this is true, sir?
Sorry?
It can be true, na, sir? Also, sir.
Yeah, so that's why. But I don't, I don't have a feeling it can be true. F prime on a compact set is always bounded. So, okay, so I'll think and then tell you in the next session maybe. Okay, so let leave this question as of now. So we have to find a function whose derivative on compact set is always bounded. But I feel it should not be true. I don't know. Okay, anyway, I'll look into it. Okay. Okay, so let's go to the next problem. Okay, so okay, so the next question is that suppose let f be a function in an open interval a b to r, be differentiable and unbounded. So then prove that f prime is also unbounded. F prime is unbounded on AB. So if the function is unbounded, then the derivative.
If we take the function x square sine 1 by x square.
X square. So this is what I took, right?
Yes, sir.
So
take, sir, 1 by x square, sir.
Okay, you want to put 1 by x square there.
Then it will be, sir, differentiable and will be, sir, unbounded, sir. The derivative is unbounded, sir. Then. So there will be, sir, minus 1 by x cube, sir.
Okay, so you are saying, let me write it here. So if I take x square sine 1 by x square, 0, x is non-zero, and if x is 0, so if I do f prime of x, so again at 0, like the same argument would work to give us that the derivative is 0, and at other point this is x square cos 1 by x square minus 1 by x4 and then 2x, right? Yeah, plus 2x.
Sir, minus 1 by x cube, simply, sir. Minus 2 by x cube, sir.
Minus 2 by x cube, that's it is.
Oh.
Yeah, so this is equal to, so minus 2 by x cos 1 by x square plus 2x sine 1 by x square, x is non-zero, 0 if x is 0. So clearly the derivative is unbounded. So f prime is unbounded on 0, 1. Okay, so I defined it x belong to, let me write here, here this example would work. Correct. So here the derivative was not continuous, but it was bounded. So here if I introduce 1 by x, correct, so here just a squaring here would work. Okay, yeah. Okay, so let's move to this problem. So here the function is given to be differentiable and unbounded. So you have to prove that the derivative is also unbounded. Okay, I don't know why this is, so I'll just log out from here and then I'll rejoin just a second. Okay. Yeah, now I think it's better probably. Yeah, so can you think of some way of proving f prime is unbounded? So here maybe this, so let me, so we know that it's differentiable. Okay, so what if I assume that my f prime is bounded? Then can I say that my function f is also going to be bounded? So I'm trying to prove it in the other way around. I mean, if I, so kind of contradiction. Okay, so what I'm saying is, if possible, suppose f prime is bounded. Okay, now my claim would be that f is bounded function. Okay, so now again, so if I take any x, what can I do is, sorry, so f prime of xi, so for any xy maybe I can choose, but there I cannot, no, that mean value theorem would not work. Okay, but let's try to use the just continuity, I think. Okay, so okay, let me do it in this way. So I want to show this is less than equal to something. Okay, so to use mean value theorem I can do one thing. If I add and subtract, okay, okay, then can it help? So here I'll get the derivative term f prime zeta, this would be mod x minus y, which is again bounded, plus mod fy. Okay, so if I want, so since I just want to deal with boundedness things, let me fix y. Okay, so let me write initially, so let y belonging to ab be any fixed element. Okay, so here I got, this is by mean value theorem, and now I know that this is bounded, given to be bounded because I assumed it to be bounded. So this would be m, and this again I can bound it by b minus a, and this is again something fixed quantity y. Okay, so if you want you can write y naught just to look it that is fixed. Okay, so now this is again a constant, so this proves that f is bounded on ab. Okay, so this is a contradiction because I assumed f to be unbounded. Is it fine?
Sir, where you use this mean value theorem, sir?
At this level.
In which interval, sir?
The interval is x comma is y naught comma x, right?
X
I
is
mean x comma y naught or y naught comma x. So this xi, I mean depending on which is the minimum and which is the maximum. So
there is, sir, x minus y naught, na, sir?
oh sorry, yeah, this is y naught. So this xi belong to x y naught or y naught x. Okay.
Yes, sir.
Okay, let's move to the next problem. What else? Okay, so let's see this one. So
Sir,
yeah,
sir, I have doubt, sir, in the first step, sir.
in the first step. Okay,
Yes, sir. How you written, sir, modulus of x is less than or equal to modulus of x.
Triangle inequality. By triangle inequality.
Okay, sir.
Yeah, I mean this is what I was saying. So since I want to estimate this, okay, and I want to use the differentiability also, as I said that when differentiability is given, it's better to just use the mean value theorem, because you know that the derivative is, I'm assuming derivative to be bounded. So that's why I try to do it in this way.
Yes, sir.
Okay, so the next question is that you consider a function f 1 to r given by f of x equal to 0 when x belongs to -1 0 1 when x belongs to 0 1. So the question is, can you find g can you find a function g such that g prime is equal to f?
Sir, will it also be true on the closed interval AB, sir? The above result, sir.
Sorry.
Sir, if we replace open interval by closed interval, sir? In this previous.
Here you are saying?
Yes, sir.
You are saying you want to replace the whole thing by closed interval.
Yes, sir.
No. See. This x.
Sir, we can, sir, apply, sir, the mean value theorem separately for the closed interval AB.
You're saying for A and for B.
Sir. And
I mean that would be, the point is that okay, if I'm defining it on A and B, then yeah, because f A and f B are something which is fixed value. I mean it's something real number. It's always
yes, sir,
going to
F
be.
is defined on closed interval AB, sir.
Yeah, so that will be anyway fixed value.
Yes, sir.
So I mean, so if you are writing this, I mean it follows from here itself, right? So suppose you are writing this, which is differentiable and unbound. Okay, but no, unbounded. Then you have to show f prime is bounded. So okay, so the proof would be, okay, if you want, let me write 1 or 2 line to check whether the argument would follow or not. Okay, so f is given to be differentiable and unbounded. So f of A and f of B are anyway given to be finite thing, right? Because f A and f B make sense. Now what, so this is given to be this, so f prime is unbounded on AB so you want to conclude that it's unbounded on, I think it follows, I mean just from the above case only. So okay, so your statement, you are saying that I'll assume that my function f is defined on the closed interval AB to R is differentiable and unbounded, right? This is the thing. Now since it is differentiable and unbounded, so if I just take that, so this would mean simply that if I restrict my f to AB is unbounded, right? And okay, it's differentiable also. So this will give me that f prime is unbounded on AB by just previous thing, and this in particular tells you that f prime is unbounded on whole AB, right?
Yes, sir.
And so there is nothing. So this is the main thing. When you close the interval, then you already know the FA and FB are defined anyway, so you don't have to worry about that for sure. But this is just from above only. Okay. So this is the question. Suppose you have been given some function f. So this function is given to you f. So can you find the function g such that g prime is? So you just have to find the antiderivative. So what do you think? So do you know the Darbox theorem?
Sir, I have heard about Darboux property.
Yeah, what is that property?
Sir, that the derivative assumes the
Intermediate
value,
volume, right?
Yes, sir.
So the derivative satisfies the IVP, intermediate value property.
Yes, sir.
So can you think, can you apply that result over here? It's just one liner, right? So I mean, you are saying that G prime will assume IVP. So now you say, so suppose it happens, suppose such G exists, okay? Then G prime at, let's say, half you know is 1, and G prime at minus half you know 0. So this would mean that G prime assumes any value between 1 and 0. But you know it's not possible by the definition itself. Okay, this is a contradiction. Is it okay?
Yes, sir.
Okay. Okay, so let's move to this. Okay, so consider this function. Okay, so if r to r given by f of x equals 0 if x belong to, if
Sir,
x
can
is,
show this a previous problem. Sir, f only assumes 0 and 1, sir. Na?
yeah,
Yes, sir. Okay.
0 and then 1 by q if x equals p by q, and then 0 if x is equal to 0. Okay, so the question is, okay, so check differentiability of f at 0. Okay, okay, so how to proceed with this? So for differentiability we need to make sure, sorry, so for differentiability at 0 we need to make sure that limit x going to 0 f of x minus f of 0 upon x minus 0 exist, right? So check, so for we need to check this thing. Okay, so what is this term fx minus f0 on x minus 0 is nothing but f of x upon x, right? So now it's clear that if I choose a rational sequence,
differentiable, sir.
it is differentiable, you are saying?
Yes, sir.
How?
Is it true or not, sir? First you take.
That is, you have to check, right? So it's not true, I mean saying, so see, ultimately we reached at this point that fx by x Yeah. And now you know that the fx, if I take a if I take some sequence which is from the irrational, okay, which converges to 0, then this is going to be 0. But if I take from rational,
we have to only check at rational points.
yeah, so in that case you can get some non-zero number, right? Okay, so now, so you have to evaluate limit at x going to 0. So let xn in q complement and yn in q be sequences such that this xn converges to 0, yn converges to 0. Okay, so what is f of xn upon xn? This is 0. And what is f of yn? Okay, so there is one thing I should tell. So when I'm saying this xn is from q complement, this is always defined, right? Since xn is non-zero, so I can make sense of this fraction. Okay, because xn is irrational and 0 is a rational number. But yn is converging to 0. Maybe yn can be eventually going, eventually constant sequence, or yn can be 0 at many points, right? In that case this does not make sense. Okay, so we have to choose some sequence yn which is from rational but it is not eventually constant. So in particular, let's take this 1 by n. Okay, or maybe let me write here yn equal to 1 by n. Okay, so this yn, I'm choosing this goes to 0. In this case this is always non-zero, so I can divide it by yn, and f of yn is going to be 1 by n, because this is p by q is equal to 1 by q. So this is 1 by n, and yn is also 1 by n, so this is always going to be 1. So we have got two sequences which are converging to two different limit points. So this will tell us that limit x going to 0, fx minus f0 on x minus 0 does not exist. Okay, is this fine?
Yes, sir.
Okay. So let's move to next problem. Okay, so
sir, at which values the function is differentiable?
I think if I take that, I'll have to think. So let us take any rational number. Okay, I think it won't be differentiable there also. Okay, so okay, let's check then. Okay, now let's choose some, let x belongs to q. Okay, so now again I'll take so let me see. So I need to limit x going to 0. Let me choose some x naught, f of x minus f of x naught upon x minus x naught. So x naught is from rational, so this is p by q. Okay, so this fx naught is going to be 1 by q. Okay, and this x minus p by q, so x going to x naught. Okay, so this is what we have to make sure whether this limit exists or not. Okay, so now if I take some sequence from irrational, okay, so suppose xn is from q complement such that xn converges to x naught. Okay, then this fx xn minus fx naught upon xn minus x naught would be, so this would be 0
minus 1 by q.
Minus 1 by 2, you're saying?
Yes.
How are you getting that number? So f of xn will be 0. This is 0, but xn you don't know, so this would be 1 by q this would be xn minus p by q. Yeah. Now as
we'll take limit.
But
take
this
limit
this this limit will not exist, right? Because you see the numerator is some constant which is not depending on
to infinity, na, sir.
Exactly. So that's what I'm saying. This limit is not existing. How we are getting half?
I'm not telling you, sir, that is half, sir.
Oh, okay. I thought it's half. Okay, so this is going diverging, right?
Yes.
Diverges to infinity.
Yes, sir. So derivative does not exist.
As x goes to
The
x.
derivative always, sir, we take finite limit, na, sir?
Yeah, obviously.
Sir, why we take some finite, sir?
Why because we are dealing in real number, right?
Why derivative cannot be, sir, infinity, sir?
We are dealing in whole this function, whatever I am writing, it's from the codomain is R. We are not dealing in extended real number. So infinity is not any number at all, right?
Yes, sir. Sir, in case of continuity, sir. Yes, sir.
Yeah.
Yes, sir.
Okay, so this tells you that f is not differentiable at any rational number. Okay, now you will have to check some irrational q complement. So you have to check limit x, again same thing. So in this case, let's take a sequence from now in this case there would be a
little zero, sir. I think limit will be, sir. Limit will be 0.
In this case, you are saying limit will be 0. So you are saying that limit will exist. I mean, you are saying the derivative will be exist. Let me check. The question is that this you have to check for this limit. Okay, so fx naught is 0, right? So this is 0. So fx upon this x minus x naught. Now here no. If I take xn from rational, so clearly irrational, if the limit exists, if limit does not exist, then irrational won't help, because if you take an irrational sequence, then the numerator is going to be 0 and hence you will get 0. And what if I take something from rational? So if I take xn a sequence in rational such that this xn converges to x naught, okay, so in that case f of xn, so let's say xn is pn by qn, so this would be 1 by qn, okay, and then you have pn by qn minus x naught, so you have 1 by pn minus qn x naught. Okay, so now you know that pn by qn goes to x naught, so this will tell you, so clearly this is not going, so for that I'll have to make sure if this goes to infinity, then I'm done, right? Because then it will also, I'm not done, but at least we can say that we cannot get a contradiction. So here this pn by qn goes to x naught, this would mean pn by qn minus x naught is less than epsilon, pn minus qn x naught is less than epsilon by qn. Okay,
so I think limit will not exist.
That I also think, but we'll have to prove it, right? I don't know, I'm not getting anything as of now. Okay, so let's keep this as of now. Maybe I'll see in next class. So the result should be there. Okay, so I'll discuss in the next session. Okay, so let's go to next problem. What problem should I go? Okay, so this is the problem. So x naught is in real number, x naught is non-zero, and f from R to R is differentiable at x naught. So for m belonging to R, you define the function am t. This is f t x naught minus f x naught upon this t minus 1 x naught minus m, and then you have 0 at t equal to 1. Okay, so now the question is that show that there exists m in R such that am is continuous at t equal to 1. Okay, so for that we just need to try to estimate this amt minus am1. Okay, so this amt is just this term over here. Okay, and then you have if am at 1 is 0. Oh, sorry, I forgot this m. Now this is just, so I'm using this change of variable, so we'll just use the differentiability. This was easy. This tx naught I'm replacing by y, so this will be t is equal to y by x naught minus 1 x naught minus m. So this is equal to fy minus f of x naught upon y minus x naught minus m. Okay, okay, so this is the difference what we are getting. Now what our goal is, that we want to make this term to be very small, right? And what we have been given is that this is differentiable at x naught. Okay, and this is something which is similar to that stuff. Now the only thing what we need to check is that this relation between how t is connected to 1. So here we want to make it small if my t is close to 1, and here you know that this is small when y is close to x naught. Okay, so now you can see from here that as t goes to 1, tx naught goes to y. Okay, so using this, so for let's put m equal to 0. So this you can say this is less than epsilon if t minus 1 is less than delta for m equal to 0. Okay, so a0 in particular is continuous. Okay, so a0 is continuous. This was just definition, that nothing else. Okay, so now let's come to this one. Okay, let me go to this problem. Okay, so this is what says that suppose you know that your function is c2. Okay, then you have to show that this limit h tending to 0, this fx plus h minus fx minus h minus 2fx upon h square exists. I mean this is equal to f double prime x, and the b part is that what about the converse. Okay, so how to prove this? So if you know that your function is c2, then you have this kind of another form of derivative, double derivative.
Sir, use the definition of f double dash, then use f dash definition of.
Okay, you want to go from here to here?
Yes, sir.
From this to this?
Sir, you have written
then
f of x into h, na?
uh-huh.
Or f of x minus h. Second term, sir. What is the second term? F of x plus h minus
X
f of
minus
x minus
h.
h. Or...
X minus h.
Oh.
Okay, so I think so there are many options, like many ways to do this. Okay, so from here maybe you can just pair this up. Maybe you can write this also, minus fx fx minus h. Oh, that pairing minus no plus would come. And this pairing I don't think one can do. But anyway, one easiest way is just to use L'Hopital. Okay, I mean that is the most convenient, because you just, when you differentiate it, this will be gone, so you'll have double derivative, single derivative term, and then that is equal to the double derivative that you can prove. So that is the simplest way to do it. Otherwise, what you can do, you can use Taylor's theorem as well. I mean, you can expand this term as fx plus h times f prime x, like that. Then the fx coming from here will cancel with this one of the fx. Similarly, you can do it here as well. Okay, and then you can get. Then another would be, like, I think as you were trying to hint out, that just directly use the definition. There probably there two limits will come, right? Because at first,
Sir, how can you use L'Hopital in this case, sir?
because it's 0 by 0 form, right?
How, sir?
The function is continuous.
Limit will
Oh,
go
sorry,
inside.
sorry. This is plus.
Yes, sir.
Oh,
Now
okay,
it is,
sorry.
sir.
Now you can do. Right. Okay. So I think that's why I was getting stuck here also. So here you just have to, I think you can do this, plus fx minus h minus f of x. Okay, upon h square upon h square. Like you can club this in two parts. I mean, separate it in two parts. Right. So I mean, there could be multiple ways. Okay, so either you just directly use the definition, there you will get two limits at the same time, and then you will have to deal with that. Okay, the best one is L'Hopital, or if you want, you can use Taylor's expansion as well. That would be again very easy to do. Okay, so I'm leaving this A, so just use L'Hopital or Taylor series expansion. Okay, what about B part? I think, see, this is also called central difference. Like when, if you do numerical analysis, there you discretize the derivative, and this is how you choose the approximation. That if you want to get the derivative at this point, then you use these 3 points. Okay, and then you say that f prime at xn is approximated by kind of f of xn plus 1 minus f, I mean this is xn plus 1, this is xn, and this is xn minus 1, plus fxn minus 1 minus 2 of fxn upon h square. Okay, so this is how you use in the numerical, I mean this kind of stuffs are used there in numerical analysis, right? Okay, that was just one comment. Anyway, so now the question is, what about the converse? So if the question is that if this limit exists, can you say that it is the derivative exists? I mean the f double derivative. So f is double, twice differentiable. Can you say that? Forget about C2. Can you still say that the function would be double differentiable? So maybe precisely if, sorry, if this limit h goes to 0, this exists, then f is twice differentiable. So this is the question that I'm asking. Okay, and the answer is no. Okay, and for that the function what you can take is this one. So you take, so this is the function f from -1 to 1 to r, and define it in this way: fx equal to x times mod x. Okay, why? Because see, the derivative, if I do derivative of this, I'll get mod x, which is not differentiable at 0 some way. I mean, okay, so if you want, this can be further written as this is x square if your x is positive, and minus x square if your x is negative, right? Now if you differentiate it, so f prime at x will be equal to 2x if x is greater than 0, minus 2x if x is less than 0. Okay, you can put equal to as well. Okay, and for, I mean, for 0 you can prove it separately. So fx minus f0 on x minus 0, if you do, you'll get x, right? Or plus minus x basically. So again the limit will exist, that's all. So limit x going to 0, x going to 0 mod x, which is 0. Okay, so you will get the derivative for this function. But now if you go for the second derivative, so this is nothing but 2 times mod x. Now this will tell you that f double prime 0 does not exist.
Yes, sir.
Okay, so this approximation or this kind of equality will hold only if the function is given to be differentiable. Oh, sorry, I did not check for this one. Okay, this thing just here. So f of x plus h minus fx minus h minus, okay, so I'll check at 0 because I know that f double prime 0 does not exist. So let me check at 0. So f0 plus h minus f of minus h minus 2 of f0 upon h square. Okay, so this is equal to f of h would be this
2,
h
2.
square.
This will be 2.
Yeah, it will add up to 2h square and then you will get 2. So okay, if you want, you can directly write this is equal to 2. Okay, so then this limit exists. So this limit h going to 0 exists, but it is not differentiable. Okay, so let's go to the next problem. So what else?
Sir,
Yeah.
sir, by applying the definition of sir f double dash, sir, we cannot prove, I think, that sir, because then this will be if and only if, sir. If you use the definition of f double dash to prove this one.
No, but there you are using that limit exists. See, when can you write f double dash x equal to that limit?
Yes, sir. Yes, sir.
So if you know that the derivative exists, then only you can say that.
Yes, sir.
Okay. Okay, so let's come to this problem. So here, let f is from 0 infinity to r be twice differentiable such that f double prime is bounded on 0 infinity and this limit x going to infinity f of x is 0. So you have to prove that limit x going to infinity f prime of x is also 0. Okay, so if your function, so again this function is vanishing at infinity, so you have to prove that the derivative vanishes at infinity as well, using the fact that double derivative is bounded. Okay, so in such cases, what one should first think is that we can try to use this Taylor's theorem, because there I can expand my given function in terms of its derivatives. Okay, and I have so I want to get some estimate for the derivative that I want to show that it goes to 0. That means it is very small. Okay, so here we'll try to do that only. So since I want to show that this f this thing is, so maybe I can write it as f of x plus h, let's say. Then if I expand it through x, so I'll get fx. So let me first write, then I'll get h times f prime x, and then I'll get h square by 2 and some f double prime x plus theta h kind of thing, where theta is between 0 and 1, right? So now you can see that I want information on this thing, and I know something about this, that fx goes to 0. I also know that this is bounded. Okay, so my goal would be to write f prime in terms of these things, and then we can think that whether it can be solved or not. So here I can write this f prime of x as f of x plus h minus f of x by h, and then plus h by 2 f double prime x plus, let me write zeta. Okay, this is what I get. Now here if you see, if I want to just take mod, because I want to estimate this f prime modulus of it, so I'll get here f of x plus h minus f of x by h. Okay, here in fact maybe here, since I want to use the thing that vanishes at infinity, so I'll take x to be very large, and that would make this and this to be large. So maybe I can just use triangle inequality. So let me write that. So 1 by h or f of x plus h minus f of x. Okay, if you want you can add plus as well. Okay, we'll see. And this is h by 2 f double prime. So this I can write it as m, right? Now this I can make it a small epsilon by 2 if my h is less than 2 epsilon by m. Okay, and this you see, okay, let me write here mod, this term and this term, if I take my x to be very large, then these terms are going to 0. Okay, so whatever h I choose, so from here I get a restriction on h. Okay, so for so maybe I'll fix my h. Okay, so fix h naught, which is strictly less than 2 epsilon by m. Okay, then f prime of x is equal to 1 by h naught. Okay, and this mod of f x plus h naught plus mod of fx plus epsilon by 2. Now this thing I know, this I can make it less than epsilon by 2 h naught, right? Sorry, h naught will be above, so epsilon h naught by 2. Why? Because I know since limit x going to infinity f of x is equal to 0. So I know this I can make it very small, whatever I want I can do that. So now this will tell me that f prime of x, okay, so this is true for all x greater than equal to some m. Okay, and this will tell me that f prime of x is less than epsilon for x greater than equal to some m. Okay, let me write some m tilde. So this tells you that limit x going to infinity f prime of x is equal to 0. Okay, I hope this is clear. It's just an application of Taylor's theorem.
Sir, from where you have introduced epsilon, that is the
epsilon is some, initially you choose this epsilon. Right, so why I choose this? Because I want to show that this limit is equal to 0, and for that what do I need to show? That modulus of f prime x will be small, I mean less than epsilon. So that's why I have to fix some epsilon initially, and then I have to proceed with this.
Sir, from the third line, sir. The modulus of f dash x plus should be sir less than or equal to, na? Because you have.
Yeah, sorry. There I am using triangle inequality. Yes.
Not triangle, boundedness of f double dash.
Here I am using boundedness. Here I am using this triangle inequality.
Yes, sir. Okay. Then, sir, fix h naught less than 2 epsilon. Why we need to fix h naught, sir?
Because see, here I just want to deal with what? I just want to deal with x. H should not come into the picture, right? So suppose here, if I want to write the definition, what do I need to show? That f prime of x is less than epsilon for x greater than equal to m. This is what I need to show, right? So h should, there is no h here.
Yes, sir.
Now, where this h is playing a role in making this term small, right? Because I know the double derivative is bounded. So to make sure that this is very small, I have to choose my h to be sufficiently small. So depending on what epsilon I am choosing, I'll have to choose h according to that.
Yes, sir.
Okay, so then that will make this term very small as per our need. How much small I want, I can make it depending on epsilon. So I want to make it, if I choose epsilon, then I want to make it less than epsilon by 2 because I have some extra term as well. So here I am using the strength of h, and here I am using the fact that fx is going to 0 as x goes to infinity.
Yes.
Okay. So I have to choose h sufficiently small, and fixing is because I don't want to get confused with this 1 by h, because if you think it seems that h is going to 0, but h is not actually going to 0. I am choosing very small h, that's all. Okay. Okay, so what? Let me go to the next question. So you know this thing, right? That the derivative of inverse function is equal to 1 by, I mean this kind of thing. That f inverse derivative is equal to 1 by f prime c kind of thing. Do you know this kind of formula?
No, sir.
Okay, then let me precise. So this is one of the theorems. So let me write. Okay, so let me make it as a question. Okay, so let I subset of R be an interval, and let f from I to R be strictly monotone. So strictly monotone will make it injective. Okay, so injective, this would imply, and continuous on I. Let G be a function from fi to I, okay, which is subset of R. Wait, it's already written. B inverse of f of f. Okay, so now this is the thing. If f is differentiable at some c belonging to the interval I, and f prime at c is non-zero, then show that G is differentiable at fc, and this G prime at fc is equal to 1 by f prime at c. Okay, in short, like if you want to remember, it's like this, that inverse derivative of inverse is derivative inverse, but this inverse is the inverse map, and this inverse means 1 by f prime. Okay, So okay, so the proof is standard, so you just have to use just the fact that this f is given to be differentiable at c. Okay, so
sir, condition of strictly monotone, sir, can be replaced by injective.
I don't think. Okay, I'm just saying that why I wrote this injective is because I want to say that this G inverse, I mean inverse
Yes,
function
sir.
exists.
Okay, sir.
Okay, so strictly monotone will imply injective, and I'm taking restriction on the codomain, the domain to be the image of f, so it will be bijective, the function, and hence the
Sir,
G
when
inverse will
you
exist.
say any interval, it means you are taking open interval, na, sir?
I
Okay.
mean it's true for even closed. Okay, it's true for closed.
Okay, sir.
uh, yeah, it should not be any problem. Okay, okay, so let me write what is given to you. So I know that f uh, is differentiable at c, so that means f prime c is equal to limit x going to c f of x minus f of c x minus c. Now my goal is to show that g is differentiable at fc, so limit uh, let's say y going to fc, g of y minus g of fc upon y minus fc. This is, I need to show that this exists. Okay, this should be our first goal, and then we'll say that this is equal to inverse of 1 by f prime c. Okay, so for that, so let y belong to the image set. So this gy is defined on the domain of g's, and the domain of g is fi. So let, if I choose my f y to be from f of I, this implies y is equal to f of x for some x. Okay, so now let me try to write this gy minus g of f of c, y minus f of c, this would be equal to g of fx minus g of fc upon fx minus fc. Okay, now the thing is that f is given to be so where is it, f prime c is non-zero. Okay, moreover, so okay, so here what I need to do, let me first write this, then maybe, so here I want to say this limit y should go to fc. Okay, and here also the same thing, that limit kind of f of x goes to f of c, this kind of thing I'll have to write, right? Now this f, I know f is given to be differentiable, right, at c, so it is continuous also at c at this point. So I can say that so okay, so there are two things. So the first thing is that f is uh, here I think I'll have to use this fact that this, the inverse what I'm getting is also continuous at f of c. Okay, g. Okay, so this will be a consequence of the fact that this it's these assumption whatever we have made. Okay, so using this assumption you can prove that g is continuous at g of c. Now why I'm saying this, because you see here I want to somehow so I know x going to c will imply f of x goes to f of c. Okay, now I need the converse also, because I want to remove this kind of limit, I want to come to the picture this one. Okay, because I'll use the fact that f prime c exists, I mean this derivative exists. So there I would say that fx converges to fc implies that g of fx, okay, converges to g of fc, right? Okay, so let me write one more line over here just to be clear. So this is, so g of fx would be x, and g of fc would be c, right? So we want f of x goes to f of c. This would be x minus c upon fx minus fc. Okay, now this fact, using this fact, I can say, that is equal to saying, maybe I can remove this g of x as x. Okay, so this is due to continuity of f at c, and this is due to the continuity of g at fc. Okay, since g is continuous at fc. Okay, now this will imply that this limit I can replace by x by c, because what does these things is telling me? This is equivalent to saying that x goes to c if and only if fx goes to fc. Okay, so I can now write this as limit x going to c, x minus c. Okay, let me write it as reciprocal. Okay, and this I know that this derivative, this limit exists. Okay, and also it's given to be non-zero, right? This thing, so this is also given to be non-zero. So now then I can use the algebra of limits, okay, to write this is equal to 1 by f prime at c. Okay, so here, so you understood the proof as of now. This is the proof.
So if fx is fx goes to fc, then because g is continuous at fc, then g of f of x will go to g of f of c. So we can replace g of f by g of f of x by x and g of f of f.
No. This is obvious. This is, here you don't need anything. Okay, this is just the definition. G is inverse.
In the bracket, sir. In the bracket, sir.
Yeah, in the bracket, yes. So here I am saying,
you have used correct. G is continuous at fc.
Okay,
so how you got sir x tends to c when fx tends to sir f of c?
Okay, so I erased it. So let me rewrite it again. So here this says that g of fx goes to g of fc.
Yes, that is what I.
And what is your g of f? Its identity, right? Because g is. So this tells you that x goes to c.
C, yes, yes.
Okay. Let me discuss one more problem probably. Let me see what to discuss. Okay, this is a very small problem, but it looks interesting at first sight. So suppose f is a function from R to R such that f of x minus f of y, okay, is less than equal to x minus y whole square. Okay, and prove f is constant. So can you tell how?
Sorry, we are able to show that f dash x is at 0, then we can.
Exactly, and that is clear from this only, right?
Yes, sir.
You just divide it by x minus y and then you get it.
Yes.
Okay, so this fx minus fy upon x minus y is nothing but mod x minus y minus x.
So there is x minus y whole square or modulus of x minus y whole square?
Whatever, it doesn't matter. This is same thing, right?
Yes, sir, this is same thing.
Okay, now just sandwich theorem gives. Okay. Okay, so this is true for any alpha for alpha greater than 1. Strictly greater than 1. Okay. write two more problem.
Sir, what if we replace modulus x minus y whole square by 3, sir, power?
Yeah, the same thing. I'm saying this is true for any alpha. If you take alpha greater than 1, that then you will get the thing, right?
Oh.
Okay. So I might just let me just write 2. But this is true for any alpha. Okay, now next question. Okay, let me do this one. So this so if be any differentiable function, so this is just an application of this mean value theorem, and let f of 0 equal to 0, f of 2 equals to 2 1. Okay, then prove that there exists C in the interval 0 2 such that f prime C is equal to 0. Okay, so it's kind of, so here what you need to do is you will first apply mean value theorem here, then you will get that at some point the derivative is becoming positive, and here you will find a point where the derivative is becoming positive, and then you can use the Darboux theorem to say that there exists a point C where the derivative is 0.
Yes.
Okay, so I'll just maybe f prime of zeta 1 f1 minus f0 upon 1 minus 0, this is 2, and if I mean there exists some, I'm writing whatever you understood, zeta 1 belong to 0 1, f prime zeta 2 f2 minus f1, this is minus 1 less than 0. So by Darboux theorem there exists zeta such that f prime and zeta is equal to 0. Okay, so let's go to one more problem. So do you know this generalized mean value theorem?
Generalized mean value theorem.
I mean the two functions, it's something like this, that f prime of zeta g
upon the g prime of, yes, sir.
Oh?
fx minus, yes.
Yeah? Okay, so I'll not write this. So let's write this problem. Okay, so let f be any twice differentiable function on AB, and f a equals f of b equals 0, and f of c is less than 0 for some c belonging to AB. Prove that there exists zeta in AB such that f double prime at zeta is strictly greater than 0. Okay, so again, like here we'll just use this, what do you say, a mean value theorem. Okay, so the f of a, where is it? So you know this a, c is there, and b. So first use mean value theorem here, then here, and then among that derivative, just as like, okay, so in before we use Darboux theorem, but here we will have to use mean value theorem because we want to prove it positive. Okay, so there exists some zeta 1 in AC such that this f prime of zeta 1 is fc minus fa. Okay, fa is 0, so fc upon c minus a. Now fc is given to be negative, so this is negative. There exists zeta 2 in c comma b such that f prime of zeta 2 is equal to minus fc upon b minus c, which is again, this is positive. So you have got zeta 1 somewhere here, zeta 2 here. So again I'll use some zeta there. So if zeta, so there exists zeta belonging to zeta 1, zeta 2 such that f double prime at zeta is equal to f zeta 2. Okay, so which is okay,
F prime.
sorry, f prime minus f prime zeta 1 zeta 2 minus zeta 1, and this is positive, this is positive, I mean negative, so this whole thing is positive and this is positive. This implies f double prime zeta is positive. Okay. Okay, so let's do one problem from this R2. That would be last problem. Okay, so from R2 let's take the differentiability. Yeah, okay, so let's do you have something to say?
No.
Okay, so then let's do one problem from higher dimension. So suppose this is the function f of xy, xy upon y square, xy belonging to R2 minus 0 0 0 if x equal to y equal to 0. So comment about differentiability at 0. Okay, so what can you say?
Sir, if it is not continuous at 0.
So it is not differentiable, right?
Yes, sir.
So if is not continuous, so it's at 0 0, and hence it is not differentiable. Okay. Now what about the partial derivative at 0 0? Will it exist?
0, all are 0.
This is equal to 0. Okay, so this was an example of not differentiable function, okay, but whose partial derivative exists. Now let us look at this f of xy equals to this x square plus y square sine of 1 by x square y square when x y is not equal to 0 0 and 0 when x y equal to 0 0. Okay, so here you have to, okay, so find df at 0 0. Okay, so let's calculate the derivative of this function at 0 0. Okay, so how do you calculate? So this f of, for derivative I need to know that this f of xy, sorry, f of x plus y plus k, I need to take the this and I'll have to approximate it by, so it's kind of like what you see analogous definition in R, kind of from Taylor series, how you define it, right? So I want to
fx.
Yeah, so h, and then you take the first derivative, then you do the second derivative. Okay, so here, so let me put x naught y naught, so that this, again I'll take the partial derivative with respect to y.
Yes.
X naught y naught, and then
by
what next?
h square delta 2 f.
But what h square?
H square delta 2 f by delta x square plus k square delta 2 by delta k delta y2.
I mean, if you want, you can go with this, but I think from here only you can conclude. Okay, so I missed, I think, one term. Where is this fx naught? Sorry. This is f of x naught y naught is also there, right? So what I'm trying to say, sorry, this plus, that this thing, okay, if you see this
Sir,
term, when
minus,
you
sir,
expand,
minus, sir, that minus term,
minus term,
there is a extra bracket, sir. Minus, there is extra bracket.
no, I am saying minus with this whole thing.
No, sir. Sir, f of x naught y naught is with that, sir. F of x naught is plus x y naught plus k minus f of x naught y naught.
So when I am taking minus common, it's minus with this and this also.
Okay.
Okay. So what I'm saying, that we know that if when I in one variable, when I expand this Taylor series, this is fx plus f prime x, right, h plus h square by 2, but I can even write order of some h, like this is how we do. I mean, this like kind of, if I just differentiate at till first derivative, this is how I get, right? So similar to this, I'll get this, and then here I'll have to divide it by the norm, right, h square plus k square, and here I'll have to show that this term goes to 0.
Yes.
Right? So the goal would be, I like to show that this goes to 0. Okay. So now here I want to show it at 0 0. So
why you have taken sir modulus, sir?
Okay, if you just deal with that, I mean, so here I am just trying to say that this estimate, so I don't want to make, what do you say, with whether it's plus minus kind of thing. So if modulus goes to 0, that interior thing also goes to 0.
Okay.
So it's the same thing, not an issue. So I want to get at 0 0, so f of hk minus this f at 0 0 will be 0 minus fx, sorry, h times fx at 0 0 plus k of fy at 0 0, right, by root h square plus k square. Okay, now if you calculate fx at 0 0, okay, what will you get? So x plus h 0, h square will be here, right? So that would be 0. So this will be 0, again this will be 0. So you just get this f of hk, which is h square plus k square, and then sine of 1 by h square plus k square, and then root of h square plus k square modulus. This is less than equal to root h square plus k square times 1, and I know this goes to 0, so this has to go to 0. So it is differentiable. Okay.
Also use here polar coordinates, na?
Also I can use polar coordinates to check the differentiability, right? Because this is in the fashion x square plus y square. So you do the substitution, you'll get that. So it will become to one variable kind of thing, right?
No, sir, it will go to 0, sir.
No, I'm saying when you do this transformation, that would be one variable function.
Yes, sir.
That is the advantage. Otherwise, why do you do that? Because this x square plus y square will become r square. This is again r square. So there is nothing like theta. So it's like just one variable thing. So no differentiability. Okay. Okay, so that's all for today. So today we left one problem, right, which was this one, to check differentiability at irrational point. Okay, that I'll try, and then maybe if I okay, so I'll discuss in the next class, or I'll just write it here and upload it on the this good drive what you have access to.